Welcome to Auto 155 Electricity and Electronics 1. My name is Tony DeBlasi, and in this lecture I will be covering the charging system. This is part 2 of a 2-part lecture based on Chapter 54 from the Automotive Technology, Principles, Diagnosis, and Service 6th edition. For additional information on this topic, please read this chapter and refer to the PowerPoint found in the course content folder. Please note that there are both audio and visual lecture attendance codes scattered throughout this lecture. Please write these codes down as you see and hear them. At the completion of this lecture, you will be required to go to the assignment folder and take the online lecture attendance quiz in order to get credit for attending this lecture. As AC current is produced inside of the alternator, we obviously can't allow AC out to the battery and the electronics of the vehicle. That would be quite destructive, and a battery cannot store AC anyways. It can only store DC. We need to change that AC signal to a DC signal, and that's referred to as rectification. This is a rectifier in this picture here, and they contain 6 diodes, and we're going to get into why they need 6 diodes, and that's because they have 3 phases and there's 2 diodes per phase. So to better explain how phases work, in this example, as this rotor were to spin, this magnet right here that I'm circling with my mouse, as that were to spin within the phase, the A and the B, as you can see here, the A being the positive side and the B being the negative side, is essentially one coil, and that would be referred to as one phase. If we only had one phase, things wouldn't work very well. I'm going to show you an animation I made years ago that helps to explain this. Chapter 54, Lecture Code Question number 6. Please write this down. 48971. Once again, that's 48971. Please write this down. So what we're looking at is we're looking at voltage over time. So this is essentially going to be a waveform. So we're starting here at 0 volts, going up to, let's say our alternator is designed to output at 14.4 volts. Obviously, if we have AC voltage, this is going to be positive, then negative, right? So as that rotor turns inside of the stator, it's going to produce a positive voltage, and as the rotor completes its revolution, it's going to pull down and it's going to create a negative voltage. We cannot allow anything out of the alternator that is negative. We have to keep it all DC. So if we were to have one phase, like I showed you a moment ago with that circuit with an A side and a B side, it would look like this. So we would have a wave coming out where as the rotor turned, it would be positive, and as it continued to turn, it would dip down to 0 and then go below to negative and then come back up again as the rotor continued to turn. So this is over a period of time. Well, we can't allow AC voltage out, so that's why we have diodes. Diodes are a one-way check valve for electricity. So we would force the current to flow into a diode rectifier bridge. So there would be essentially one diode here and another diode here. So that would be 2 diodes for this one single phase. Well, imagine if I'm the battery and I've got power coming out and it hits 0, it would be off for a moment. So think of it this way. If I only had one phase, my alternator would be on, off, on, off. That's why we have additional phases to help fill in the gaps. So if I were to mount a second phase, being the green one, by the time the first phase were to drop, the second phase would come back on to help fill in the gap. Well, the only thing missing now would be a third phase. With 3 phases, being the yellow one being the third phase, I'm able to continue a nice steady DC current. I'm establishing that DC current. Now the problem that we run into is we have these gaps. So this kind of a wavy form here still, where it kind of it's 14.4 and then maybe it dips down to 14.1 or 13.9. So these gaps right here, we refer to that as ripple, and that's the blue little sections here are filling it in. That's where the battery comes in. So as the alternator is feeding its DC, its rectified DC current into the battery then acts as a capacitor. And remember, we discussed that a capacitor absorbs fluctuations in voltage. So that's its job. So the battery helps smooth out that signal from the alternator. Now, to further discuss how rectification works, we are going to go back to the Films on Demand. There is a section there that discusses rectification.
Rectification uses diodes to convert alternating current into direct current. A diode is simply a one-way electrical check valve. With electron theory, a diode will conduct current when forward biased. Note how the current or electron flow is blocked when it tries to flow through the diode reverse biased. When forward biased, a diode will conduct direct current. If polarity is reversed, the diode will block current, and this basic circuit would not function. This scope waveform shows alternating current. Alternating current has the polarity swing positive and then negative. Current flows one way, then the other way through the circuit. A diode will block current in one direction and then pass half of the AC current in the other direction. Since only half of the sine wave is conducted through a single diode, it is termed half-wave rectification and is not power efficient. Full-wave rectification passes both the positive and negative halves of the AC sine wave and is very efficient. An alternator rectifier uses multiple diodes to pass all of the AC current and convert it into direct current. This 4-diode diagram represents the fundamental action inside the alternator diodes. A scope connected to the output of this circuit would show full-wave rectification. Most alternators use 6 diodes to convert the stator AC into DC output for the car's electrical system. A heatsink is often used to dissipate heat and protect the diodes from damage. Wires leading out of the diode block solder or connect to the 3 wires at the stator. This animation demonstrates the basic action of a diode block. As the alternator rotor turns, its magnetic flux cuts across and induces an alternating current into the stator windings. The AC is represented by the small balls of light or electrons moving back and forth from the stator output wires. The diode block converts the AC into DC. This is shown by the electrons flowing in only one direction, out of the alternator. This cutaway shows the rotor spinning inside the stator and front and rear housing. Also, note the brush holder mounted over the slip rings. This front view shows the drive pulley and fan. Picture how the fan would throw air outward, pulling air through the inside of the alternator to cool internal parts.
With regard to rectification, I want to discuss 2 types of stator connections, and that's the Y and the delta. The Y-type stator winding, otherwise known as the star type, is the most commonly used type of stator connection. The output current with a Y-type stator connection is constant over a broad alternator speed range. In a Y-type stator connection, the currents must be combined because the 2 windings are always connected in series. The delta winding is connected in a triangular shape. Delta is the Greek letter shaped like a triangle, so that's how it gets its name. Current induced in each winding flows into the diodes in a parallel circuit. More current can flow through the 2 parallel circuits than can flow through a series circuit, like in the Y example. Delta-connected stators are used on alternators where high output at alternator revolutions per minute is required. A delta-connected alternator can produce 73% more current than the same alternator with a Y-type stator connection. For example, if an alternator with a Y-connected stator can produce 55 amperes, the same alternator with a delta-connected stator winding can produce 73% more, or 95 amperes. The delta-connected alternator, however, produces lower current at low speeds and must be operated at high speeds to produce its maximum output. Chapter 54, Lecture Code question number 8. Please write this down. 41341. Once again, that's 41341. Please write this down. As stated at the very beginning of this lecture, as far as the induced voltage and current go, they are basically relying on three factors. Those factors are the speed of the rotation, or the engine RPMs, the number of conductors within the alternator, so in other words, the windings inside the actual armature itself, or the windings in the stator. Also, the strength of the magnetic field. So in other words, the more current that I can flow through my armature, the more magnetic field it will have, and that will equate to more power coming from my stator. In this example, there's a picture of a stator, and if you look closely, you'll see it doesn't have 3 phases or 3 coils. This one actually has 6. So we've discussed rectification, in other words, changing AC to DC, and how it's done and how it's wired. I'd like to take a little time to explain voltage regulation. So an alternator can make a lot of voltage if we do not regulate it, or if a device doesn't, or a system doesn't regulate it. It can put way too many volts out into the system, and that could cause damage to our battery and our electronics. So this has to be regulated. So this occurs, or this happens, by controlling the field side of the armature, or the actual rotor itself. So the control of the field current is accomplished by opening and closing the ground. So once again, we have a ground side switch. And this is on most alternators, not all. Some of them do control the power side of the armature. This is done by the use of a very special kind of diode that we refer to as a Zener diode. A Zener diode can block current flow until a specific voltage is reached. Then, once that voltage parameter is reached, it permits current to flow across it. This is the heart and the soul of voltage regulation, or I should say solid state voltage regulation. In a moment, I'm going to play a video from Films on Demand that will show the 3 different types of voltage regulation that are out there: mechanical, remote solid state, and then internal. Well, they left out a 4th one, probably because the video is slightly dated, but nowadays it's remote again, but it's being done through either the body control module or some type of charging module that's responsible for charging system voltage. In some cases, and we'll talk some more about computer-controlled charging systems, based on the battery's condition, it can actually affect the charging system voltage and amperage rates. One of the things that you may come across, and we discussed this in the battery section, was battery registration. So based on how long the battery's been in the vehicle or when it was last installed, you may have to perform a reset procedure to let the charging system know just how old the battery is. Voltage regulators can compensate for temperature as well. So this is a PowerPoint slide that I made many years ago to try to summarize how voltage regulation works. So if you'll notice the yellow box here that says voltage regulation, notice that it's a module on the ground side. So this is a ground side switch system. We're going to either give ground or take ground away. If you follow into the actual alternator itself, you'll notice the 2 little brushes. The ground brush, its ability to get ground and complete the circuit is interrupted by the voltage regulator. So the voltage regulator is going to control that. Now the voltage regulator needs to know if system voltage is just right. We call it the Goldilocks zone. Is it too high? Is it too low? Or is it just right? So the voltage regulator is going to reach out using the battery sense circuit. So it's going to use a sensor. And that sensor is going to determine what is my voltage level. Right now, if my voltage is too high, the switch will be open and no power will be made. So the alternator will be cycled off. Well, if voltage gets too low, then the voltage regulator will flip the switch, causing the alternator to turn on or cycle on, making power for a moment. So it will induce voltage using a very powerful magnet in the rotor. Then the voltage regulator will reach out, check it again. If it gets high, it'll turn it off. So you notice how that switch just keeps cycling on and off. Now, if you noticed, a fun fact just popped up over here. Voltage regulators can cycle the field circuit on and off between 10 and 7,000 times per second. So that's its duty cycle. Obviously, if a battery is low in voltage, it's going to be cycled on more often. If it's where it's supposed to be, if it's 12.6 or higher, then the voltage regulator will cycle on less often. This image shows an internal voltage regulator. It's very, very small, fits in the palm of your hand. It's loaded into the brush end housing or the slip ring end housing of the alternator. And you can see the circuit board there. It's coated in a thick film or a thick jelly to keep it from overheating. So that's one of the problems of putting these in the alternator. They can get hot and they can fail. But these are pretty reliable. This is a diagram of the circuitry that's in the voltage regulator. And you'll notice the way that the stator is wound, it is a Y winding. So there's your stator in the lower left-hand corner. And this is basically the circuit that controls the regulation of voltage. Now you'll notice there are two transistors, and we haven't really gotten into what transistors are. Think of them like solid state relays. They can either turn something on or turn something off based on inputs. You'll notice there's a diode that looks different than all the other diodes. That is the Zener diode. And that diode, as I said before, will allow current to flow once a certain voltage parameter is reached, which essentially gives this system the ability to function. So it's kind of the brains or the traffic cop behind whether the alternator provides voltage or cycles on or cycles off. Chapter 54, Electric Code question number 9. Please write this down. 56489. Once again, that's 56489. Please write this down. At this point, let's take a look at the films on demand. This will be our final video for the charging system.
As its name implies, a voltage regulator limits the amount of voltage and current generated by the alternator. Without regulation, an alternator could overcharge the battery, evaporating its electrolyte, or it could burn itself up from overheating. 3 types of voltage regulators have been used over the years to control the output of the AC generator. Years ago, a contact point type regulator was used to control the alternator. A large set of contact points operated by magnetic coil action were used to open and close the circuit to the rotor as a means of controlling output. When voltage reached a preset value, the coil would act on the points to open or stop current flow to the rotor windings. Then, when voltage dropped, the points would snap closed to energize the rotor. This provided a crude means of voltage regulation. The next improvement was the remote solid-state voltage regulator. Note the electrical terminal for connecting to the stator, field, battery, and indicator light. This allowed the remote regulator to sense output and adjust it up or down as needed. It allowed the regulator to turn on a warning light if voltage dropped too low. The electronic regulator has the tiny electric circuit sealed in a protective gel. We have removed the protective gel to expose the internal circuitry of this regulator. Note how much smaller and simpler this is than the older contact point regulator. Here is a modern internal voltage regulator. It usually mounts inside the alternator. Some designs mount on the rear outside of the alternator. Basically, an electronic voltage regulator controls charge output by turning the field or rotor current on and off. If the field current is on 90% of the time, this would increase charging voltage and current. If the field current is on only 10% of the time, it would reduce charging voltage and current. Study how the alternator and its diodes are wired to the voltage regulator. Transistors inside the regulator are designed to cycle the rotor field on and off depending upon load. The dash indicator light is often wired so that if voltage drops below battery voltage, current will flow through the indicator light to warn the driver of a problem. Voltage regulator circuit designs vary. Normally, battery voltage is 12.6 volts. To charge the battery and to operate the electrical system properly, the alternator should generate 13 to 14.5 volts. Charging amps can vary from a low of 35 amps up to 80 or more amps. Specifications are sometimes stamped on the alternator, or they'll be given in the service manual. This animation shows the basic action of a regulator. During normal operation, the regulator cycles the field on and off to maintain the correct charge voltage. If charge voltage drops, the regulator increases field current. If charge voltage is too high, the regulator decreases field current. If something is wrong with the charging system, current flow is directed to the dash indicator light to warn the driver of trouble.
We're going to wrap up our presentation or our lecture by going over two more considerations, and one is alternator cooling, and then we'll talk about computer-controlled alternator function. With alternator cooling, there are many different ways of trying to keep it cool, because obviously turning a rotor on and off is going to generate heat. The stator itself is going to generate heat from current being induced through it or voltage being induced through it. The diodes are going to generate heat by rectifying the AC voltage to DC voltage. So obviously heat is a major concern with a charging system. So cooling that charging system is very, very important. Now, up here I've got a few examples. We have an external fan, which I believe was in that breakdown or that mock-up of the alternator, but they also have internal fans. So you'll have a fan inside the case to pull heat out, and the external fan to help pull cool air in and also assist in pulling heat out. The other thing that GM tried for a while, and I'm not sure about any other manufacturers, they actually would run coolant lines into the alternator themselves. In fact, I have a picture right here of what that alternator looked like. So you can see there's two connections for coolant hoses. But ultimately, to keep the alternator running cool is to control its internal armature circuit or rotor circuit. And that is best done with some logic. So there is no better logic than using a computer to do it. So beyond the actual voltage regulator itself, computers can sense and they can actuate. So the three ways that a computer can communicate or factor in would be that it can activate the charging system by turning on and off the field current to the rotor itself. The computer can also monitor the operation of the alternator and increase engine speed or decrease engine speed depending on if it needs more or less RPMs, especially at idle. The computer can also control the alternator by controlling alternator output to match the needs of the electrical system. On a cold morning, you have your headlights on, your windshield wipers, your rear defrost, your heated seats, heated steering wheel, you have everything turned on in the car, but the alternator can't quite match what is required. Then it will do a thing called load shedding, where it might reduce the amount of amperage required to the rear defrost. When normally it would get 100% of amperage, now it's getting 90% of amperage or 80% of amperage. That would be referred to as load shedding. Some of the other neat stuff in part of the control or the logic that the computers use, the theory of operation, is they look at temperature. So a computer, a PCM, BCM module, whatever, would use the intake air temperature to determine how to charge back the battery or how to operate the system. In this example, there's a current clamp or a current sensor acts like an inductive amp clamp, where, I'll bring my mouse in, you can actually see this Hall effect or inductive clamp that is around the positive terminal. This is here so that the charging system or the computer that controls the charging system can monitor current that's flowing from the battery, mostly during power off or key out of the ignition. So we would once again refer to that as parasitic draw. It's also looking at open circuit voltage or state of charge of the battery. If the computer has these two items or these two data points, then it can effectively charge the battery and perform all of its other duties as well. This slide does a pretty good job of demonstrating duty cycle. In the upper picture, it shows an off time of 10% and an on time of 90%. This is a square waveform. In the lower picture, it shows an on time of 10%, but an off time of 90%. Obviously, the one on the bottom is kind of a desired condition, where the alternator or generator isn't running as often as it would need to be, because first off, the driver of the vehicle doesn't have every load on, or the battery's at a full state of charge. So essentially, the duty cycle is lower. But these are the types of things you need to understand before you begin evaluating a charging system circuit. You need to know its strategy or its theory of operation so that you can make an accurate diagnosis. This chart provides an example of duty cycle based on alternator output voltage. So you can see along the left-hand side where it displays the percentage of cycle time, and on the right-hand side you can see the direct result of how many volts are coming out based on its duty cycle. This concludes the Part 2 lecture for Chapter 54, the charging system. For additional information on this topic, please read this chapter and refer to the PowerPoint found in the course content folder. Now that you have completed this lecture and you have written down the online lecture attendance codes, please go to the assignment folder and take the online lecture attendance quiz in order to get credit for attending this lecture.